To understand global evolutionary trends, a researcher must reconcile the massive scale of planetary biology with the microscopic detail of a single organism in the wild. Take Lepidodactylus vanuatuensis, an endemic species of gecko found exclusively in Vanuatu. In the context of a field survey, this lizard represents a discrete, isolated unit of data. But to integrate that gecko into macroecology, it must cross a massive structural divide. This dataset on the right is the Shy-Mary 2008 Index, a compendium of body sizes for thousands of distinct lizard species. The mathematical objective of such a dataset is to compile arrays of divergent organisms into a single cohesive model. To accurately compare species across different geographic zones and distinct evolutionary clades, researchers must establish a standardized morphological metric. For the Vanuatu gecko to contribute to this global model, its dimensions must be recorded using a universally compatible metric. The intuitive assumption is that measuring an animal's size simply means measuring it from head to tail. However, for squamates, this approach is biologically flawed. The first complication is tail autotomy, an evolutionary adaptation where many lizards literally shed their tails to evade an attacking predator. Relying on total length introduces massive amounts of statistical noise. A single predator encounter instantly alters an organism's recorded size, even though its core biomass remains exactly the same. The second complication is the extreme natural variance in tail-to-body ratios across different reptilian lineages. An arboreal species with a long prehensile tail and a short-tailed terrestrial species might share the exact same core physiological mass, yet they produce radically different total length measurements. These fluctuations mean total length is a variable that obscures true evolutionary comparisons, making it a mathematically unstable metric for global modeling. The solution to this instability is Snout-Vent Length, or SVL. It's the bedrock metric of herpetology. Snout-vent length is the distance from the snout tip to the cloaca, the vent. This isolates the organism's primary biological mass, capturing just the head and torso. Discarding tail data lets researchers focus on the lizard's stable central morphology. Universally applying SVL allows for a one-to-one comparison of core biological size across all species, regardless of their tail condition. We can see this standard deployed at scale by looking at the architecture of the MARY dataset. The matrix groups these isolated SVL values precisely by Linnaean taxonomy, categorizing organisms by family, genus, and species. Ultimately, SVL reduces messy anatomical variations into a clean, global dataset that is completely immune to localized morphological quirks. This section isolates the Agamidae family, the dragon lizards. Within this single evolutionary clade, the body size divergence captured by SVL is extreme. At the lower end, Ceratophora carew records an SVL of exactly 33.7 millimeters. This measurement identifies the gecko as a highly specialized microendemic organism. The upper extreme within the same family is Hydrosaurus amboinensis, which has an SVL of 350 millimeters. The data shows that Hydrosaurus possesses a core biological mass more than 10 times greater than its relative Ceratophora. This massive quantitative gap represents millions of years of divergent ecological pressures, driving these species into entirely distinct environmental niche adaptations. Because SVL ignores the noise of tail morphology, it can reliably quantify this tenfold evolutionary stretch. Shifting the analysis to the Anguate family reveals how the metric handles even more radical anatomical differences. Look at the measurements for Anguis fragilis at 290 millimeters and Ophisaurus ventralis at 306 millimeters. These species are predominantly legless glass lizards. Despite entirely lacking limbs, their core biomass can be directly compared to a four-legged dragon lizard because SVL measures the same anatomical chassis in both. Moving down to the Chameleonidae family matrix, the dwarf chameleons of the Brocasia genus bottom out at an SVL of just 19.5 millimeters. These minimum SVL values allow researchers to document precise instances of insular dwarfism in global size modeling. Comparing the large, legless burrower to a microscopic arboreal chameleon, the measurement standard remains identical. SVL links these vast biological differences. It strips away legs and tails, comparing only the fundamental physical frame. Looking at the record in its entirety, the list of species aggregates into a massive mathematical matrix of pure comparative data. When these values are plotted on a scatter plot, researchers can begin to uncover macroecological trends. Clustering thousands of SVL data points reveals deep, continent-spanning geographical and environmental patterns of body size evolution. This trendline demonstrates the strict correlation between ambient temperature and core body mass. The outliers on this graph dictate exactly where researchers must look next for new evolutionary explanations. This matrix of numbers serves as the indispensable bridge connecting localized taxonomy to predictive global modeling. Every single coordinate on that global scatterplot originated as an isolated field observation. It returns to the specific classification of Lepidodactylus Vanuatuensis. Cataloging the precise SVL of one endemic gecko in Vanuatu is the absolute prerequisite for understanding global reptilian divergence. The entire field of macroecology is bound by the rigor of its base morphological metrics. Without the standardization of snout-vent length, the immense complexity of squamate evolution would remain computationally opaque. Rigorous, unglamorous data collection, measuring exactly from snout to vent, is the foundational engine driving modern evolutionary biology.